When I was a kid, I always wanted to learn assembly language. So, what better way than to do something really hard? I'm also a moderate space nerd, so I thought, why not try and combine this yearning to learn assembly with space nerdiness? So no matter what age you are, join me on my journey to recreate the Apollo DISCI user interface for the Apollo guidance computer on a Commodore Vic 20.
Working in verb 35, I think it is. We see a real display now.
Why buy just a video game from Atari or Intellivision? Invest in the wonder computer of the 1980s for under $300. The Commodore Vic 20. Unlike games, it has a real computer keyboard. With the Commodore Vic 20, the whole family can learn computing at home. Plays great games, too. Under $300, the wonder computer of the 1980s, the Commodore Vic 20.
Now there's 20 years that separates the tech between the Commodore Vic 20 and the Apollo's guidance computer. But in many ways, the way they work is quite similar. The hardware's quite different, but the programming language actually shares a lot of commonality. So a programmer from those days would probably recognise and understand the code from the 1980s, for example. Now, the chances are that you're watching this video because you're either A, space nerd, or B, interested in 8-bit computing. But maybe, just maybe, it's possible that you don't know anything about either of those things. So let's first of all talk about what is a DISCI and what is the Apollo guidance computer. Well, quite simply, the Apollo guidance computer, or AGC as it's sometimes known, is the very, very early computer that took men to the moon for the first time. It's the computer that helped Neil Armstrong and Buzz Aldrin land in July 1969 and make that journey all the way from the Earth to the moon and back safely. It isn't working. But what's a Vic 20, you might ask? Well, there's so many videos about the history of 8-bit computing. You can probably find a whole really in-depth video about the history of the Commodore Vic 20. But put simply, and the reason I made this video, is it's my first 8-bit computer that I had when I was about 10, 11 years old. Got one second-hand from my brother's friend. It was one of the first computers to be mass-produced and mass-marketed at consumers like you and me. So when I was young, that's why I had one in my bedroom, and it drove and spearheaded a whole computing revolution alongside other machines like the ZX81, the ZX Spectrum, later the Commodore 64, which was really the son of the Vic 20, if you like. So why do I love the Vic? It's my first machine, as I've said many times before, and I always wanted to learn assembly and to learn how to what I call programming properly at the lowest level possible. Well, almost the lowest level possible. So that's the Commodore Vic 20 in a nutshell. It's still out there today. People still make games for it. Idiots like me make videos for it. So why bring the two together and try and emulate an Apollo DISCI on a Vic 20? Well, why not? Got to have a hobby, haven't I? My Vic 20 lives upstairs, actually, and I haven't actually been using it very much. Most of the work that I've done has been in the Vice emulator using the CBM PRG Studio software from Arthur Jorgensen, which is a must for any Vic 20 developer out there. But here's my Vic in all its glory. Dun, 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 dun. That's what's going to run the DISCI on this here display. Display, keyboard. DISCI, display, keyboard. No joystick on this one. Yep, there's my Lego Apollo Saturn V. But let me make one thing pretty clear from the outset. I'm not trying to create a Vic 20 version of the entire Apollo guidance computer. just the diskie, and that's important because the diskie is only the equivalent of the mouse, keyboard and monitor of the vehicles that took men to the moon for the first time. So let's look at some key facts about the diskie. One of the things is that it was the place the astronauts got alerted of alarms. Another is that it had a simple keyboard. So using it had to be pretty straightforward. Imagine trying to land on the moon, having a problem. You don't want to have to remember how to press a whole sequence of buttons. So the designers of the diskie made it as easy to use for the astronauts as they could. And as I said, the diskie comes from a time when fully digital computers were in their infancy. There were very few integrated circuits, and in fact, the Apollo missions were one of the first times that integrated circuits were used. In fact, they were the reason that integrated circuits like silicon chips that you are all using today were actually created. So, it's not so much about clever digital electronics inside the diskie. It's more about old school stuff. So it's less about zeros and ones and ones and zeros and ones. It's more about analog switches, things called relays that turn lights on and off. Channels, remote control, things that we're familiar with, but things that the Apollo guidance computer had.
Microwaves, brilliant!
And channels, input-output channels, were the way that the diskie communicated with the actual main Apollo guidance computer unit. It's fascinating stuff. And you know how I came across this stuff and became fascinated with it was from another channel, an amazing YouTube channel run by a bunch of guys, and the channel head is Curious Mark. He's an absolute legend. And if you haven't watched those videos, the Apollo AGC restoration series, then you must go and check them out. They are the source of inspiration for this video and the videos to come. Thank you, Mark. So I suppose with this video series, one of the questions that's in the back of my mind is, could an 8-bit computer of the 1980s taken men to the moon? And I think the answer is probably yes, because although the AGC had very limited processing power and memory, and people always say that old adage about, you know, you got more processing power in your mobile phone than took men to the moon, which is all true, but it was all about the design and the way they were frugal with what they had and what they could use. So that to me is really interesting. So if we had a 35k VIC-20, could it be an AGC? Could it link up to our little diskie VIC-20? And that's all far in the future episodes. But it's intriguing, isn't it? So join me on this journey, won't you? So, cool enough. But how did Neil and Buzz interact with their computer? So let's rewind back in time a little bit and think about the size of computers in the 1960s and the early 1960s, really, when the Apollo missions were being planned. Now, you might have seen videos where they show the very first early computers that took up enormous rooms full of people feeding in punched cards into arcane looking devices with blinking lights on them. That wouldn't have been any good to try and launch into orbit, would it? A whole room full of kit. So what the designers at NASA and their contractors had to come up with was something far more advanced and something miniaturized, tiny, in fact, compared to the equivalent computers of the day. And they did that. And as we said earlier, if you're flying around in a spacecraft, you know, you want things to be as simple as possible. In fact, any aircraft are designed to be as simple as possible to use. So the designers of the diskie, the display and keyboard input for the Apollo guidance computer kind of took things back to first principles, the first principles of language. So one of the basic things that you learn at school about language are things like verbs, doing words, and nouns, naming words. And actually, they're the fundamental things, the very basic things about communication. If you're in a foreign country and you're hungry and you're looking for somewhere to eat, how do you go up to someone and ask? You might say, well, you might do some sign language and point at your mouth and rub your tummy. And you get a funny look probably. But you'd probably like to say, I want to go eat, you know, or need food. Simple communication. And verbs and nouns work that way. And the way that the astronauts communicated with the Apollo guidance computer was very simple in that way. The disky itself had only 19 keys. Some of them were special keys. And you could press a verb button and then type in a number code to enter a verb. And then you could also enter, in a similar way, a noun. So you could say, you know, land being the verb and spacecraft being the noun. Now, it didn't actually work like that, but you get the idea. Very, very simple way of controlling things. And I guess in a later episode, we'll get into some of those nouns and verbs. But for now, that's an intro into what the disky actually is. Now, this is Frank O'Brien's excellent book on the Apollo guidance computer. It's really been my Bible, and again, more source of inspiration for the project that I'm doing here. And here's a diagram of the disky. You can see those 19 keys. And obviously, well, maybe not so obviously, we won't actually be modelling those in the VIC-20. We're just going to use the VIC's keyboard. It's one of the kind of things I've decided that we'll do. But what we will be trying to recreate is the upper portion here. So the electroluminescent displays that show the program, the verb, the noun, and then the three data elements there which tell the astronauts key bits of information relating to the program that's running. And then over here we've got status indicator lights, and really getting those lights to flash is what I've spent the last few months doing. And I do mean the last few months, because this has not been an easy project. I don't think I've got the right kind of brain for assembly, really. It's, I don't know, it's too mnemonic, it's too short, and I'm better with high level languages. And I'm not the best programmer in the world, I'll be the first to admit. So that's probably why it's taken me longer to get where I am, which is, you know, an important milestone for me that I celebrated recently. But, you know, it's still enormous fun, even when it's frustrating, even when I'm sitting there scratching my head and almost wearing a hole in my head, scratching my head, trying to figure out what normally to me would be really simple things when programming seem much more difficult in assembly. Margaret Hamilton, the lead developer on the AGC, actually coined the term software engineering while working on the project. Now, on the lunar module of the Apollo spacecraft was one disky, and in the command module there were two, and they were placed centrally, especially in the lunar module, right in your face, so that easily accessible for the astronauts to get up and running and to key in those vital commands. Now, all the indicator lights that you'll see on that left hand panel of the disky are actually controlled completely by the software. Whether they are turned on or off is completely determined by the AGC software, making changes to indicator bits within the input-output channels that it writes to for the disky. And you'll see, if you do a little research, that there are different sets of lights on different diskies. Now, the reason for that is that the command module and the lunar module had different uses for the lights, and the lunar module had a couple of additional lights in the out altitude and velocity lights. And some of the lights were used in slightly different ways depending on the application. So what do all those cool looking lights do? Well, like any light, it's switched on and off, and for various reasons. So for example, there's an indicator lamp for uplink activity on the Disky, and that's only lit when the ground station that the either lunar module or command module is in touch with is uplinking data. Could be just an update of the system clock on the AGC computer, or other reasons that the ground staff would take control of the AGC remotely. And that's when the uplink activity light will switch on. The temp light, yeah, temp stands for temperature. Now that was used to indicate not if it was too hot or too cold in the cabin where the astronauts sat. No, it was something else. It was one of the instruments, the inertial measurement unit. It had a very sensitive operating range for temperature, something like 126 to 134 degrees Fahrenheit, I believe. So if the system, the sensors in the spacecraft detected that the inertial measurement unit had gone outside that range, either too hot or too cold, then the AGC software would light the temp light to let the astronauts know that there was a potential problem brewing with the IMU. Now, the inertial measurement unit was an absolutely vital piece of hardware within the spacecrafts. Now, it was used to determine the velocity, the speed, the vector, the direction that the spacecraft were going in. So you can imagine that if there was no reading coming from that vital piece of hardware, you would need to let your astronauts know pretty quick so that they could try to rectify or troubleshoot. So the NO-ATT, or no ATT, stands for no attitude light, would light up if there was a problem with the hardware associated with measuring the attitude or the orientation of the spacecraft in question, and you see a no ATT light blink. And there were certain things the astronauts could do to rectify that. They could try to reset the IMU system, or the system, or the problem could have been with one of the other boxes of tricks, the coupling data unit, which kind of sat between the IMU and the AGC and the Disky as a kind of hub for some of that data, sending it in the right direction, and also for some of the other sensors on the spacecraft. So that was no ATT. Basically it means I don't know which way I'm pointing. Help! Now, if you hang around people that talk about rockets, eventually somebody will mention the term gimbal. And quite often that is in relation to the orientation of a rocket nozzle. Basically, it's how you steer a rocket. You can gimbal, i.e. kind of rotate through certain degrees of motion, a rocket nozzle to point a rocket in the right direction. So rockets don't go just straight up, they do steer through the atmosphere and obviously in space. And sometimes if you watch a video and a rocket goes out of control, you'll see those rocket engines trying to correct the course of the craft by gimbaling. Now, a gimbal is 3 concentric rings mounted inside each other, which can be used to work out the angle between them and therefore give the attitude of the spacecraft. Now we come to the gimbal lock light, and I'm going to need to sit down for this one because it's slightly complicated. So the gimbal lock light It's nothing to do with engine gimballing, as you might naturally expect. It's more about the internals of the gimbals that make up the inside of the internal measurement unit. And there is such a scenario where the spacecraft can be oriented in such a way that two of the gimbals become aligned together, locked effectively, and then no matter what you do to turn the spacecraft, they won't unlock. So the gimbal lock light on the AGC Disky was designed to warn the astronauts when the Z-axis went too far one way and was about to align with one of the other axes and become locked, therefore causing a gimbal lock, which you didn't want to happen, particularly if you were busy in a spacecraft. You didn't want that to happen. So the gimbal lock light is there to stop that from happening. So what the astronauts flying the craft could do would be to take some corrective action before they got into a gimbal lock situation, and they would, you know, it wasn't necessarily unrecoverable as long as they had the time and the space, forgive the pun, to correct whatever was going wrong in the IMU with those gimbals. So it's more of a warning light to get them out, keep them out of trouble, than one that's telling them they are in trouble. Useful though. Yeah, the standby light. Yeah, standby light was just used to basically let the astronauts know that the system was in standby, powered down. So in the situation of Apollo 13, where they had to conserve the power, we've all seen the movie, conserve the power going across the buses within a spacecraft, then you may choose to put the AGC into a lower power mode, and I think that's when the standby light would come on. Pretty easy really. Now the prog light would be used if there was an issue with a particular program and it was trying to tell the astronauts that something was wrong through an alarm, a program alarm. Now famously there were a couple of those that occurred during the initial ascent to the moon with Apollo 11, with Neil and Buzz. It's quite a famous scenario. Wasn't actually a problem with the AGC computer, it was behaving flawlessly, people have since found out. Doing what it was supposed to do. It was lighting the program alarm light, simply because there was too much data coming into the AGC and it couldn't handle it all. And this was because the rendezvous radar for the lunar module, that was only used really on ascent when trying to rendezvous back with the command module, that was left on during the descent. And so there was too much radar data trying to be processed by the good old AGC. And rather than just give out a blue screen of death, what it did was lit the program alarm, told the astronauts that there was a 1201 and a 1202, which are quite similar issues. And the ground engineers made a call during that ascent that it was okay to continue. Now, as it turned out, that was the case. And the skill, the manual piloting skill of the legend that was Neil Armstrong, got him and his co-pilot Buzz Aldrin down onto the lunar surface safely. But I think if you keep an eye on the Curious Mark channel, I'm certainly keeping an eye on it, one of their future videos will go into recreating that scenario, and they'll be able to dig into exactly what was going on and was it really such a safe decision to proceed. As it turned out, all was well, but given more information, would the guys on the ground have made the same decision? We'll see. Keep your eyes on the Curious Mark channel for that one. But there you are anyway, that's the prog light, which is basically telling you something's wrong. So the next light you might see illuminated on your Disky, should you ever find yourself in an Apollo craft on your way to and from the moon, is key rel, or key release. And what that is basically telling the astronauts is that there is a program waiting for their input. So the machine may be busy, the AGC may be busy processing, but it actually wants something to be keyed in. So it's asking the astronauts to do that, to do the key release and to give the instruction that the AGC is asking for. So that's key release, key rel. Now if the AGC has encountered an error, which means that it needs to restart to recover from it, then it will light the restart light. Now we all make mistakes, and the astronauts were no exception to that. And although the verb-noun system of communicating with the AGC through the DSKY is pretty straightforward and simple really, it could still be, in certain scenarios, done wrong. And if the operator had made an error, then guess what? The OPR, ERR, or operator error light would blink on until the astronaut had corrected the issue with whatever verb-noun combination they were trying to use. The tracker light on the lunar module was used to let the astronauts know that there was a problem with the rendezvous, the lunar landing radar, that they could no longer work out their altitude and probably also velocity. And in that case, linked to the tracker light would also be the alt and vel, altitude and velocity issue lights, that would blink on if the nasty scenario occurred where the landing radar was malfunctioning or the moon had disappeared. Who knows?
I'm a bit idle really right now, and sometimes so is the AGC. And when it wasn't busy processing, the comp activity light on the right hand side of the panel would be extinguished. In fact, it was when there was a dummy task running, just the computer doing nothing, idling along. That's when the comp activity light would be turned off. It would be turned on when processing began again. Pretty simple really for a light that tells you when your computer's busy and when it's not. These days we have hourglasses and things that go round and round and round. Those blue rings, where did they come from? When did they become a thing? I think a comp activity light would be much more preferable, don't you?
So they, on the left-hand panel of lights, plus the comp activity light on the other side, that I've tried to replicate and at least make flash for milestone 1 of the DSKY on the Commodore Vic 20. Round of applause? Okay, suit yourselves. It's probably time that I stop waffling and we actually have a look at some code and what I've done and how I was thinking about creating an analogue of the DSKY on the Vic 20. Let's go take a look.
So before we start looking at the code, it's just occurred to me, I mentioned earlier how long this has taken me so far. So let's just have a look and see when, on what date the project file for the Vic DSKY was actually created. I think it's this file here, DSKY1. And let's see if we look at the properties of the file, when it was actually first created. 1st of August 2022. Now I did say that I haven't been working on this full time, but you know, it's taken me a long time because learning assembly is hard. Well, at least I'm finding it hard, but I'm getting there, and let's show you how I am getting there. So let's take a tour first of all of, I suppose, the memory map and some of the things that we're using to emulate the AGC and the connection between the DSKY and the AGC, I should really say. So, because we're not, remember, we are only doing a DSKY, we're not doing an AGC. So, various variables here to start with that are useful, like a constant to store the first location on the screen RAM, which I use when I'm drawing the screen, and various other useful sort of, you might call them admin variables. These variables here, 0 page pointers on the VIC-20. If you know coding on the VIC-20, you'll know what I mean by a 0 page pointer. It's useful for writing to the screen in an efficient way, without having to worry about high bytes and low bytes too much. Go look it up if you don't know what I mean. It's quite interesting. Do a bit of Googling. But anyway, once I got my head around that unlocked a lot of stuff. So then I've got a few variables which are not being used yet, but these will hopefully later be, long way down the road, be locations in memory where, if let's say we manage to get to the stage where we've got another VIC-20 which is pretending to be an AGC, then this would be the place where the data would go in and out, a buffer for the data going in and out of the disk key. That might change in the future, but it's just a low byte and a high byte location for input, and the same for output. So we will see how that goes. I might end up putting bits in there which are masked in the future, but I'm getting way ahead of myself there. But that's the kind of architectural thinking that I've got going on in my head. So then we've got another bunch of memory locations here that you can see, which I'm just using to store either a 0 for this light is on, that I'm using to store a 1 for this light is on, or a 0 for this light is off, and they are directly related to the different lights on that disky panel, which we'll see in a minute how that's been represented. So noughts and ones, basically ons and offs. Then I'm thinking ahead again, haven't got this far, but a byte to store the program number, or the major mode as they would have called it back then, and the verb that's being interacted with, and the noun that's being interacted with on the disky by the astronaut. Then you've got the numeric light registers, the actual numeric displays, and again I've used a high byte low byte combination of 2 bytes next to each other that I'll be using again down the track. Haven't got there yet. Then again a bit of kind of utility stuff. So what I ultimately want to do is to use interrupts to go and look at memory locations and check whether a lamp on the disk key should be on or off, and if it is, run the routine which refreshes the display based on those bits being 1 or 0 on or off for the various lamps, and then return control to the VIC-20. That's, I want that to happen a few, I guess, I don't know how many cycles, how often we're going to do that. I thought we could maybe use the cursor flash timer to do that, but I'm not sure, because that actually you need the cursor turned on to do that, and that's going to be difficult to have a flashing cursor in the top left corner. But it could be we use the screen raster timing to do that. I've been doing a little reading on that. Again, I'm a newbie, so forgive me, but maybe I can do that way in terms of the timing of the screen display, how often we actually do that. Anyway, that'll be probably in episode 2. But for now, we just have a single variable that says, has something on the display changed, which I'm manually keeping track of and setting and unsetting. It gets unset when the display is written, but it gets set when I change one of the 1s or 0s on one of the lamp indicator memory locations. Then again, we've got some admin variables really that I'm just using to keep track of things and to toggle things on and off, and just temporary variables really, I guess you'd call these. So that's a few bits of memory that we're using, and let's just quickly show you the character set.
Because you are a character doesn't mean that you have character.
So yeah, we have to think about the disk key as just an input and output device. As I said earlier, just like your computer monitor or your mouse or your keyboard, disk keys are really just input-output devices, peripheral, if you like, to the main Apollo guidance computer. But of course, when you're trying to replicate a real-world object in a computer, like we're trying to do here with the Disky inside the old 8-bit VIC-20, you know, you've got to take a few liberties, and you've got to try and, I think, model as closely or encapsulate the real object as closely as you can. So one of the first things I thought about was, well, how am I going to represent the Disky on the screen? If you know anything about early 8-bit computers and things like the VIC-20, then you'll know that some of them had quite limited graphics capabilities, and the VIC-20 is no exception to that. And actually well, there are other ways to do it, but the main way and the simplest way, certainly for a kind of newbie assembly programmer like me, is to redefine the characters. So like any 8-bit computer, you press a key on the keyboard, a character comes up on the display. Now you can, through code, redefine those characters, and you can do simple things like animations. You can make tiles, and if you're into creating games, that's something a lot of people have probably already done. So one of the first things I had to do was think about how I'm going to represent what the Disky actually looks like as a real world object inside the VIC-20. So first of all, the Vic, as standard, has got some quite good characters for drawing little screens. So the basic framework of the Disky display was quite easy to do, with a few circles and dots and straight lines and a few corner edges. Not too much of a problem. But then when it came to representing the lights and the luminescent displays, I needed to redefine some characters, and to actually redefine characters to represent more than one character in many cases. So kind of creating little tiles that would represent things like the comp activity light.
Beautiful character set designer from Arthur here, and as you can see, as you'll see in a moment anyway, these are the little elements on the display that will form the lights, these little tiles. For example, we've got TE and then MP there for temp, GI, MB, AL there across 4 characters for gimbal as the part of the gimbal lock light. So we've got reverse video versions of each of those as well, and I'm only using the first 72 characters, just trying to be as frugal with memory as possible, really. So that's the tiles, the characters that I've created. Then let's show you how those look on the actual Disky display itself in this little screen design. Here it is. So we're just mirroring or recreating the top panel of the Disky. So the keyboard, remember, will be underneath, but it'll actually be the VIC-20 keyboard that we're using. It's only a limited screen size on the Vic. I know you can change resolution and things like that, but again, that's all a little bit beyond me at the minute. So I'm trying to keep things simple. So you can see here each of these little areas with the characters. So the uplink activity light, the computer activity light. These will be the indicator lamps on the Disky, and you can tell that this is a lunar module Disky. Were you paying attention? We've got the altitude and velocity lights that you only get on the lunar module Disky for the landing radar, I think, if I remember rightly. And then we've got the program, verb and noun that will be holding the numerics, the numeric display that maps back to that memory location we saw a minute ago. And then under here will be the luminescent strips, the kind of digital little displays that I think they, from watching Curious Mark, they make a clicking sound as they come on and off. So I was thinking the other day, can I replicate that? We will see. Again, probably episode 6. Who knows? In about 2025, the way I'm going here.
The next challenge, once we'd drawn the screen, and wow, was there some celebrating when I actually managed to do that correctly for the first time, was to actually think about, well, how am I going to make these lights, these different indicator lights that the Disky has, that are so vital to the astronauts, the feedback from the computer. How are we going to get that output to display on the screen in a way that looks, you know, kind of realistic? How are we going to flash those lights? So that was the next challenge. Now, one of the big challenges when you're programming in an 8-bit computer environment with a machine like the VIC-20 is memory. Now, the unexpanded VIC-20 has only got 3.5K. And that should be enough, in all honesty, to recreate something that looks and feels and acts a little bit like a disky. Remember, we're modeling hardware in software here. So what we did to try and make that a reality was think about the layout of the memory that we were going to use in the VIC and where we were going to store certain pieces of data. So for example, there are a lot of in the real disky, as I mentioned earlier, these relays that fire on and off and turn lights and lamps on and off. And these relays are going to be modelled as bits, 1 or 0, on or off, inside the VIC's memory. So we had to create lots of data structures for those. We had to create many data structures just to map around the screen so we knew where to go to turn a light or change a colour on a screen or flip a character from its normal look to its reverse video look. All of that had to be loaded and mapped into the VIC's memory so that we could access it with the assembly language program. So lots to think about, much more to think about when you're trying to do something like this in assembly language than you would normally have to think about. But great fun. It makes you really work in a way that's as memory efficient as possible, because you really do need to save every byte of RAM, because it won't be long before you start to run out. Because when you start to redefine character sets and store screen definitions in 3.5K, you can quite quickly start to consume and use up lots of that actual memory, and we don't want to run out. We don't want to run out of memory and have an overflow when we're trying to land on the moon, do we?
So this is the map of where each of those indicator lamps, so if you remember the uplink activity, the comp activity, they have got a memory location where they start. It's kind of like an offset location where they start, and they're all 2x4 in terms of the number of screen locations used to create the little light. So that's the way I've coded it. So the first one, which was the what? The first one is, I need to load the character setting again, don't I? The first one is, of course, uplink activity. Uplink activity and temp. So uplink activity starts at screen location 7726 and 7748 is where temp will start. Now you'll notice I'm using the greater than operator, which is saying that this is the high byte of that screen location, and down here I'm doing the opposite and it's the low byte. So I need to read those basically like a lookup table to find where I need to write the various bits as I go through the routine that refreshes the screen. Then we've got an included binary here for the character set, and also similarly an included binary here for the screen design that I just showed you.
So like all good programmers, I made a memory map, and that helped me to know, you know, because it wasn't every day that I was working on this. I can't work on this every day, it would drive me crazy. But in between programming sessions, the documentation I could keep leafing through and going back to, so that I knew where I'd got to in terms of the memory map, and it changed over time as I learned and made lots of mistakes, because this has been very much trial and error.
So in terms of code itself, not much actually here, really. Probably too much, probably more than there needs to be, but forgive me, keep saying it. But first of all, we just set things up. We clear the screen. We run the code that defines or redefines the character set. We set the screen and background colors, and then we initialize the screen of the disky display as it is, which is down here. Jump down to init screw. Here it is, and that literally just sets the text color first of all, and then it initializes the 0-page pointers to get ready to start drawing the screen itself. And then we have another routine. I'll zip back up. We have another routine which is called and that is this one here, out screen, or OUTSCR as I'm calling it. And that basically just reads that definition of that binary file that is assembled into the final program, and it goes through writing each character onto the screen. This took me ages to figure out how to do, and there's a guy called Grey Defender whose videos I watched, so shout out to you, my friend. You were doing a PAC Man clone, and I watched your video a few times to try and get my head around it. You were doing it on a Commodore 64, I was doing it on a Vic 20, but the coding's pretty much the same. So I actually learned a lot from you, my friend. So thank you. You were learning at the time, and you taught me. So be proud of that, and I'll hopefully send you a message, and you'll know you've helped someone out there in the world of Commodore Retro.
But one of the great things about the Vic 20 is the community around it still. There's a forum called Denial, which there's a bunch of guys on there who have always been ready to help me with my newbie assembly language programming questions on the Vic 20. So Mike in particular on the Denial forum, kudos for you for getting me this far. Mike actually sent me back to Vic 20 school. He's got some great tutorial lessons for learning assembly language on the Denial forum. Some of those threads have been around for years, but they're still teaching newbies like me how to code in assembly even to this day. So yes, I created the Flapping Birds program in assembly and really enjoyed it, and actually doing that on the actual Vic hardware itself was a brilliant lesson to learn.
So this is a pretty simple routine really, and it literally just draws the screen. Now I've over commented because I'm a newbie probably here, but literally each line of code I've commented. The bit that really I thought was clever, again I learnt this from another person in the community, a guy Chisholm I think his name is, over on the Denial forum. We were talking about writing to the screen, and I was saying how can I easily flip from the screen memory on the Vic 20 to the color memory, because they're two separate memory locations that I have to write to. How can I wanted to make my code as efficient as possible. So little tip that I learned here was toggling between the screen RAM location and the color RAM location just by using an EOR command. Not Winnie the Pooh, no, of course, we all know it's an exclusive OR, and I'm using the number 88 to slip between, say, 7680 and 38400, which is the first location of screen and the first location of color memory, flipping backwards and forwards. Now, you need to be careful when you're using this technique, as Mike wisely pointed out later in a thread, because you can get mixed up as to where you've got to in terms of your toggle. But I've been okay so far, and I'm only using it in kind of one routine right now, so hopefully it will be okay. So yeah, that's my output to the screen code, and then I go back to the sort of initializing area of the program at the start. I then at the moment calling this routine after I've initialized the screen called reset lights, and what that does is basically loops through all those ones and zeros, all those bytes that I've set up to be the memory locations that are going to store the state of each light, whether it's on or off. Now, where is that code? Where is my reset lights code? Where have you gone? reset lights. Here we are. So we literally, in this small routine, looping through all of those memory locations that start with uplink. If you remember, that's the first light. We've got the X offset there, and we're just starting at number 13, the last one, and we're going backwards through down to 0, and we're just basically storing a 0 in each location, and then we're telling the system or telling the program that the display needs to be updated, i.e. it's dirty, and then we're ready. The lights are reset, they're all turned off, and we can go ahead and call the main program. Forgive me for jumping and skipping around here. The main program is here. So at the minute, all we're doing is calling the light check routine, and literally all that does is cycle through each of the lights, and it first of all turns the light on, and then it turns it off. So we've got kind of a loop within a loop. We've got a loop of 2 within a loop of, it's actually a loop of 13 for each light. But because each light is made up of 2 rows of characters, we have to go around twice. There's actually a loop of 26 here that we're calling, or looping round, I should say. So yeah, so this routine, pretty simple, just goes through and turn the lights on and off. But believe me, when I got this to work for the first time, I was over the moon. It was awesome, and that was a couple of weeks ago now, to be honest. So yeah, and what was the key thing I learned here? Probably the key thing I learned was, there was one thing that got me scratching my head. I, for some reason, was thinking that I was using the RTS command in the wrong place, and I was dropping out of a subroutine because I was thinking that it was like a return in a Go sub in basic, rather than dropping out of the subroutine, which is what it actually does. And when I realised my mistake, I just kicked myself because I was sat there for about 2 days trying to figure out why this code wasn't working, and that's what it was. But that's kind of what I'm up against here, because this is all very unfamiliar territory. So the actual main guts of this so far is the blink lights routine here. Again, probably longer than it needs to be, but it basically loops through each of our lamps and checks to see whether it's currently on or off, and compares with the status bit in memory as to whether it should be on or off. And then if it needs to turn it on because it's off, it will. But if it's already on, it won't try and turn it on again. So it's got that little bit of logic in it. And it flips to turn things on. We simply flip to the reverse version of the character that we're looking at or about to turn on or off on the display. And we change it from color 0, which is black, to color 7, which is yellow on the VIC-20. And that's pretty straightforward, really. Again, the logic and the loop in here took me a while to figure out, because you've only got things like branch not equal or branch equal to do your loop control, which again, just a little bit difficult for a newbie like me. But we got there in the end, and I can now hopefully click. Let's click run and see if it will go. There's the assembled code. Here comes Vice. Yes, here comes Vice. There we go. So you'll notice that cursor flashing in the top left on that initial lamp test, because I'm using the cursor timer to kind of slow things down a little. Otherwise the code just runs too fast and you don't even see the lights blink on and off. So if I press escape, things should stop. We terminate nicely and return back to Vice. So that's the code so far, folks.
As you can see, the TE has started to attract away from the vehicle.
SpaceX about to do it again there. Last summer, I went on a trip
down to the seaside and visited the Ramsgate Micro Museum. I wonder if they've got a Vic 20. This is Mike, everyone, from the Ramsgate Micro Museum.
Hi there.
And I guess you're the curator. Would we call you?
Yeah, I should be curator as well as Carol.
Did this start at home as a collection and just spiral?
Well,
or?
yeah, in actual fact, what happened is I got made redundant and I was looking for something to do. I thought, oh well, I'll go and have a look around the car boots house. And I found a Dragon 32.
Oh, what a find!
Yeah, and the computer case, which is over there.
Yeah.
We've got some copies over there. And it sort of stems from there. 40 years on, and I've collected all this lot. And we've moved a few times.
Yeah.
And I was filling up the roof, the cellar, the garage, some rooms in the house, and then we had to move, and so I've got a bigger place, and it all started all over again. And it's quite surprising. In the last year or so, there have been a few people, and they've donated a few bits and pieces, but usually you find there's always something different.
Yeah.
Because the thing is, it's all sort of old technology that we've got in here, and it's a challenge just to keep it going. If it breaks down, if you have to take it for a repairing, you can be looking at that £30 to get it repaired.
Yeah.
And I've got so much, so I can afford to leave it and bring something new in, so that people can have a go on the newer stuff that I've got in the museum.
So were you kind of hobbyist and enthusiast back in the day?
What happened is I bought a ZX81, and we had it for about 6 months or a year, and I started to buy all the games for it and all the programs. And what happened was, if you typed a program in, what would happen is, if you got up to make a cup of coffee and you knocked it, it would lose its memory.
Right.
And I used to call it round-packed wobble, and it was famous for the Sinclairs to doing that. And then I thought, well, I'd like to get a ZX80 because they were being superseded by the ZX81, and I found one, and so I went all the way from East London over to Sipson Village, and I bought one, and I paid £15 for it, which is quite a good price to pay for one of those.
Yeah.
3 weeks later, I came home and went down to car boot sale, found one for £3.
Typical.
Typical. But anyway, it's a question of I've been looking around for a Commodore 64. And it wasn't until the Amiga came out that I managed to find a Commodore 64. And so I've got a Commodore 64, and it's sort of escalated from there. Yeah. We did get a BBC Micro.
Ah, yeah. Remember this from school days?
Yeah.
And is that the Acorn as well you've got there somewhere, did I see? Yeah.
Yeah.
Yeah. Oh, there's a 480Z there. I remember those at school as well. The old 480 research machines there.
Which plays a nice little tune.
That's Captain Pugwash, if I'm not mistaken.
That's right.
Do you know, those graphics are actually better than I remember.
Yeah, it was quite good.
Yeah.
You've got the yo-yo to try and get it, and then you've got to go from one side to the other. It's a lot harder than you think.
Just look at all these consoles as well.
Yeah, these are, there's the 2600.
Yeah, the classic.
Which everybody
Yeah. My next door neighbour had one of those. We never had one. We had the Binatone, like I say, so I used to nick next door and play on that. But yeah, awesome. And there's the Dragon.
Dragon 32.
Again, I spent a lot of time with a friend of mine on one of those, playing Joust. Yeah.
I'm going to put a few games on.
Sure, mate, yeah.
We've got
Thanks for chatting. You could spend literally hours lost in nostalgia at the Micro Museum.
there's a fine array of old machines to re-familiarise yourself with and introduce your youngsters to. Absolutely incredible. And not only are there PCs, but old consoles like this Philips Video Pack, which brings back so many memories for me. And these old media that kids just don't get right.
Yeah, that's
it, is it? That's the kit Sinclair.
That's it.
Wow. And that's a little, it's a little Z80. Yeah, boy, little Z80 sitting on there as well.
Oh, it's a SCMP.
Oh, is it?
Yeah, so it's part of the stamp system. But yeah, 49 quid. It meant you could write your own code and get to do your own bits and bobs.
Yeah. And then the Jupiter must have come next, was it?
It would
the
have
Z80.
been, it would have been the ZX80. Jupiter race was 82, which was the same time as the. Where's it gone? Rubber King.
Oh, the good old 48k
specky,
didn't it? 16 or 48, yeah.
So these are all 81, 80, 81. And then
yeah. See, I graduated from a Vic 20 to one of these, one of the Amstrad versions of the Spectrum, the Plus 2.
Oh, I'm sorry to hear that.
I know, but I loved it at the time.
I think this is arguably the better Sinclair, isn't it? The Toast Rack.
Yeah, that's the 128. Yeah, a friend of mine had the Plus 3. I just saw one of those.
Yep.
Yeah.
Yeah, again, this was when Alan Sugar took over
the
6128, so you had to have the Sinclair equivalent.
That's it, yeah. This place is so cool. So we've got Vic here, have we? Yeah.
Yeah, so you got the Vic, you've got the Commodore 16 down there as well, which is quite a rare machine now.
Yeah.
Plus 4, obviously, you've got there's a 64C, 64.
Yeah. But what's amazing is that there's still people writing games titles for these. I mean, even the Plus 4 and the 16. There are people out there that are still writing code and releasing new games. It's amazing.
Well, it goes back to the same old thing, isn't it? How playable it is.
Yeah.
And if it's playable, then it's all isn't it? It's like Tetris, all these games. Pong. Yeah. You can still play them. No, that's one of our most popular. These two down here. It's one of our most popular things.
Yeah.
People queue up just to play Pong.
It's amazing.
And what was your first machine?
Yeah. Incredible. And then from the Spectrum, I didn't go ST or Amiga. I went straight to PCs. I went to DOS after that. Yeah, because by that time I was at college and learning.
Yeah, of course.
You know, so my next machine, because I actually worked at Tandy in the shop.
Oh, did you?
While I was at college.
Tandy, the thinking man's napkin.
Yeah. So exactly. Yeah. So there's a Radio Shack machine there. Yeah. And the first PC I had was a Tandy 1008X, which had a little 3.5-inch floppy drive in it and a 8088 processor. But again, I used to use that for college work. I used to run Pascal on it and write code in Pascal on that. Yeah.
These new ones are cool. These are the ones that started off the BBC literacy, computer literacy program, and they were the ones that were originally going to have the contract, and that's when Clive Sinclair and Chris Curry jumped in and said, hang on, because they're going to be favouring a certain company, so people should get a tender for it. Yeah. So these guys obviously started that, so they would have been in it. Dragon was in it. To be honest, Dragon was probably, in my opinion, would have been the second best choice, because it's quite a durable machine. Really.
Yeah, for the classroom, yeah.
Exactly, yeah.
Yeah, and I tell you what, a friend of mine, like I say, he used to play in his bedroom, play joust. And when it wasn't going his way, he would tend to lose his temper and smash that keyboard, and it survived.
Yeah, exactly. This is the shocking thing. It's crazy, isn't it?
It was amazing.
It was always Sinclair's thing, though, wasn't it? It wasn't about being the best. It was always about being first.
Yeah.
Same with the electric car and everything like that. You can't argue that he was one of the innovators for that sort of stuff and clean energy and everything.
If he was around today, just launching that, it'd be a different story.
Yeah, when you think about how far batteries have come in.
Exactly.
Yeah. Yeah, same as his watches as well. They always failed. They always napped. It was the first digital watch.
I was just looking at that calculator because I remember we had one at home very similar. So, Pete, Micro Museum, near in Ramsgate, easy to find. You'll find it on Google Maps.
Yes.
£5 to get in?
£5.
perfect to bring the kids down. I mean, this place is full of kids enjoying the old tech. And you're open when?
Saturdays and Sundays, 1 till 4, up until the end of September. But check the website and
yeah. And you're looking for donations actively all the time, I guess. So if there's anyone watching that's got something they would like to donate, maybe they're in the southeast of the UK.
Yeah, anything that's interesting, anything you find. Like someone walked in with a North Star Horizon the other day from 1979.
Whoa!
Which cost, in 1979, it was about the price of a house.
Yeah.
So you literally can either have a box this big or a house.
So I know what I'd rather have.
Yeah, exactly.
Pete, thanks a lot for walking me around. It's
yeah.
awesome.
No problem.
Cheers. So, what have we actually managed to achieve for milestone 1? Well, we've got something on the Vic that looks a little bit like a disky, the front panel at least. We've got the memory structures in place that will allow us to interact with an Apollo guidance computer or a virtual one, maybe in the future. And we're able to light portions of the screen in analog to the indicator lamps on the disky itself. So not bad for someone who didn't know any assembly language on a 6502 just 6 months ago. I'm quite pleased. Join me next time to find out how we get on with interrupts. So, the car I'm driving in now first hit the road in the year 1972. And if you're a fan of the Apollo program, then you'll know that the last manned trip to the moon so far was in 1972 with, I think, Apollo 17. So it won't be too long before man returns to the moon. NASA, supported by SpaceX and many other contractors and amazing people, hope to head there probably with a manned mission within the next, I guess, 5 years or so. But there's a lot of work to be done between now and then. But just think about how amazing it's going to be for us to sit down with our children and watch that next moon landing. I hope we get the same feeling as those lucky guys in 1969, in July 1969, when they got to witness on live TV their first ever moon landing. I think to me it's going to be as exciting and much more of a spectacle with the lunar starship from SpaceX providing the human landing system. It's going to be incredible. So that's an inspiration for my children, and I hope we can sit down and enjoy that as a family. And if you want to support this channel and you've also got children of your own that you'd like to get interested and enthused about the topic of science and space that we've been covering in this video, then please do visit my website, Winterfam, WINTERFAM, winterfam.co.uk. You can download a free short story, you can download a free audio book, get a taste of what my work is like as an author, and see what I'm trying to do in terms of inspiring the next generation of youngsters to get involved in science and technology. That's what it's all about after all. Thanks so much for watching. Hope to see you in the next one. Hopefully it won't be as long in between the two videos as the last lot. But yeah, thank you so much and see you next time.
That's a good demonstration of how crew has the interface with the